Now we're going to learn about another quantum algorithm that, while it doesn't provide as large a speed up over its classical counterpart, does still have an interesting structure that makes it worth discussing. The problem to be solved is as follows. Imagine that there's an array of n switches which all have to be set in a correct configuration W in order to light a bulb. Now, to make the problem difficult, some of these switches have been installed upside down, and there's no manual lying around, so the all-up configuration isn't necessarily correct as it should be. If we tried a certain configuration of these switches, some up, some down, it wouldn't tell us anything about which of the switches were set incorrectly. All we would see is that the bulb is either lit or not. For this problem, if we limit ourselves to classical algorithms, there's no essentially better strategy than to guess and check repeatedly until we find W, the correct configuration. This requires a number of switch flips that scales as 2 to the n, which can get quite large as n grows. To lay out the corresponding quantum algorithm, we're going to need to make use of another building block, the oracle. Oracles are used in many different quantum algorithms when the complete implementation of a given function is unknown. An oracle is a black box that we can prove is unitary, though we don't know the circuit complexity of its implementation. In place of a proper complexity, which is worked out in terms of the space and time cost of running a quantum circuit, we use the number of queries to the oracle, which is the number of times that it's used, as a proxy. The oracle for the light bulb problem will look like this. We input a configuration Z, some eigenstate in the Z basis on each qubit, and if the bulb would light up, an ancilla qubit gets flipped. Already we can see that if we input a minus state on the ancilla, we can obtain what I'll call UF, which maps W to minus W and acts as the identity on all other states in the Z basis. We can see that the operation UF can be written as the identity minus 2 times WW. If this is unclear, pause the video and take a moment to evaluate the action of this operator on the state W and on other states which are orthogonal to W. We can also define another unitary U+ that does almost the same thing, except that it acts as the identity on the all plus state and applies a -1 phase to any state orthogonal to the all plus state in the X basis. Now we're going to take the product of these two operators and call it the Grover iterate G. We're going to show in the following section that if we apply G k times to the all plus state as an input, we end up with a state that's very close to W, the state describing the winning configuration. First, let's write the all plus state out neatly. We can see that the all plus state is a uniform superposition over all states in the Z basis, and that this necessarily includes W, regardless of what W actually is. There's also another term, which is proportional to W perp, which is a uniform superposition of everything in the Z basis that's orthogonal to W. We're going to write the coefficients of this wave function as angles to simplify our calculation later on. Now we can see that the first part of G, UF, just places a minus sign on the W term. Easy enough. To see the consequence of then performing U+, though, we'll have to define another state plus perp, which is just a state that's orthogonal to the all plus state, written out using W and W perp. Now we can express UF plus in the plus perp basis using a little bit of trigonometry. Eventually, we get to the expression cosine of 2 theta plus minus sine of 2 theta plus perp. Applying U+ and changing the basis back, we can see that the Grover iterate takes our initial angle theta and replaces it with the angle 3 theta. If we did this k times in a row, we'd end up with not 3 theta, but 2k plus 1 theta. In order to obtain a state close to W then, we have to choose k so that the sign of 2k plus 1 theta is close to 1. Now, the sign is close to 1 when the angle is close to pi by 2. So this gives us a k roughly equal to pi divided by 4 theta, which is roughly pi by 4 times root 2 to the n. This scales as the square root of the number of configurations we'd have to try in the classical case, providing us with an algorithm that has a polynomial speedup over the classical one.